So we have an assemblage, say olivine, orthopyroxene and quartz. And as I said, the first thing is you should know the composition of the minerals. Now, say for example, if we can start with a simple system, MgOSiO2, where olivine is pure phosphorite, orthopyroxene pure enstatite, and quartz pure SiO2. So the system components are Mg and SiO2. So now, let us see what are the variables here. You know the variables should be pressure, temperature, fluid composition, mineral composition, pressure, temperature, one variable, fluid composition, one variable, or multiple variables, and the compositions of each of the phases. But we see here that they are all pure phases. So there is no compositional variable. So the metamorphic variables here are mainly pressure and temperature. So if there are two variables, you need two equations, and therefore there should be two reactions. Theoretically, you need them to evaluate the pressure temperature condition. Right? Let's see where we are. So now we come to the number of independent reactions is equal to number of phase components minus number of system components. So what are the phase components here? 1, 2, 3. For each, there's a phase component, phosphorite, which is pure but phase component. Mg2Si2O6, it's a pure phase component, but it has a phase component. And SiO2 is a phase component. So number of phase components is 3. What is the number of phase system component? MgOSiO2. So 2. Number of independent reactions, 1. Simple. What is the reaction? You can see here, Mg2SiO4 plus SiO2 is equal to Mg2Si2O6. That's the equation that you get. It is, now you can see, you will have only one reaction, and this is the reaction. Okay? So now, we have two metamorphic variables, but one reaction. From one reaction, you cannot find two variables. Which means, you can either find P, you have to, if P and T are the variables, from this reaction, which is also an equation in P and T, because G is equal to a function of pressure and temperature, you cannot find both. So it's going to be a univariate system, because one variable needs to be quantified. Let's see what the Gibbs phase rule says for this. Gibbs phase rule says F is equal to C minus P plus 2. Right? C is the number of system components. NS and C here are the same. So we have 2. Number of phases, olivine, orthopyroxene, quartz, minus 3 plus 2. So that's 4 minus 3 is equal to 1. As you said, it's univariate. The system is univariate. The system by itself cannot find out both pressure and temperature, but it can give you the variation of pressure and temperature in a PT space. It can do that. But it will not be able, the system cannot itself quantify T and P separately. Its P and T will be in the form of an equation. That means it will be a line. And as we rightly predicted, it is univariate. Now let's try to make it a little more complex. We take again olivine, orthopyroxene, quartz, but this time we say olivine as Mg, Fe whole twice SiO4. Orthopyroxene, of course, has to be then MgFe 2 Si2O6 and SiO2. Now, you see, this is the composition of the phases. So now your olivine is not pure anymore. Orthopyroxene is not pure anymore. Only quartz is pure. Right? So we have two solid solution phases and one pure phase. If you do that, then you can see here from this that you can have three MgO, FeO and SiO2. These are the number of system components. Have you understood? So there is a difference. What is the difference? Here it was MgO, SiO2. Now from here we have three phase components. Three system components. So if you look at this expression here, Gibbs phase rule. Let's write down now. Phases, not phase components, phases. 1 olivine, 2 orthopyroxene, 3 quartz. So once again, we have now, component now goes to become 3 minus 3 plus 2. So that will be 2. So it will be 5 minus 3. And this will be equal to 2. So Gibbs phase rule say it's a bivariant reaction. It's a bivariant system. 3 minus 3, system component is 3, system component is 3, phases, number of phases remain the same, 3 plus 2, 5 minus 3 is equal to 2. So Gibbs phase rule says the variance is 2. Now, the question, what are the metamorphic variables? What are the metamorphic variables? What are the variables that we're looking for? What variables are there? As I told you before also, pressure and temperature are two variables. So let's write it down here. Instead pressure and temperature. So we have pressure and temperature. These are the two variables, metamorphic variables. What are the other variables? Say for example here, for olivine, it's MgFe whole twice SiO4. So what is the variable? X forsterite in olivine or X firelite in olivine. Because they add up to 1. X forsterite plus X firelite in olivine is equal to 1. So this is one variable. Or. And you have X enstatite in orthopyroxene or X ferrocylite in orthopyroxene. Again this or. Why? Because X enstatite or XF Mg orthopyroxene plus XFE orthopyroxene should have to 1. So we have 1, 2, 3, 4 variables. We have 4 metamorphic variables. 4 metamorphic variables we have. We don't have any fluids here. So there are 4 metamorphic variables in a 3-component system involving 3 phases, one of which is pure. Now let's say independent reactions. Now we come to the independent. So you have to find out the variables. You have to know how many equations you have. How many equations you have. And it says you should get into a bivariant field. You should get into a bivariant field. So now we see this reaction. What are the number of phase components? Phase components, not phase. Phase component. So olivine, this phase, has 2 phase component, Mg2SiO4, Fe2SiO4. Orthopyroxene, Mg2Si2O6, Fe2SiO6, 2 phase components. And SiO2, 1 phase component. So we have number of phase components as 5. Minus number of system components which we have derived as 3. So the number of independent reactions is 2. So, IR is equal to 2, F is equal to 2, and these are the metamorphic variables that are there. which we need 4 reactions. So if you have to find out 4 variables, you need 4 reactions. But your system says, out of the 4 reactions, you have 4 variables, but you have only 2 independent reactions. So your variant should be 4 minus 2. 2. So that means 4 minus 2. Number of variables minus number of independent reactions is 2, which is the same as what Gibbs phase rule says, that there are 2 degrees of freedom. Of course, that means you have to quantify 2 of these variables to get the other 2. Right? But what are the reactions? One is, of course, this one. One is, of course, this one. Now you see there is a little small thing here. One is this one. Mg2SiO4, we have already written. You see, this is an extended system. So the other reaction is already there from MgOSiO2, that is already there. What are the others? You see, I can also write Fe2SiO4 plus SiO2 is equal to Fe2Si2O6. Now this is also an independent reaction. This is also another reaction. From this you can't derive this. Or from this you can't derive this. So you have already 2 independent reactions. But you can have another reaction. Let's say this is reaction A, this is reaction B, and you can do another reaction C. How? Let me show you. You subtract A from B. Eliminate SiO2. Eliminate SiO2. Then what will be the reaction? You see here, Mg2SiO4 plus Fe2Si2O6 is equal to Fe2SiO4 plus Mg2Si2O6. You see, this is your reaction C. You have 3 reactions possible. 3 reactions possible. How did I get this C? By algebraic addition of A and B and by eliminating SiO2. If I do this, then you have Mg2SiO4 plus Fe2Si2O6 is equal to Fe2SiO4 plus Mg2Si2O6. Have you understood? So that is very crucial. But you can see here. But this is not an independent reaction. C, as I have done it, is not an independent reaction. It's a derivative reaction. Or you can say, okay, for some reason, I will take B and C. Of course you can take B and C. Then your A is a derivative reaction. Why? Subtract B from C. You will get back to this reaction. If you subtract B from C, then you see this FeSi2, Si2O6, this will all cancel off. And you will get back A. So you can use either any two of the 3 reactions to find out the variables. You can find it out. So that is how it is. But what it says is, out of the 4, you will only get 2. You won't get more. Unless you can quantify from outside other 2 variables. That is why Gibbs phase rule is so crucial. So Gibbs phase rule tells you you have 2 inputs to be brought in. This tells you, independent reactions tells you, you have 2 reactions. 2 plus 2, 4. That is the metamorphic variable. That is the number of metamorphic variables. So the link between Gibbs phase rule here and independent reactions and metamorphic variables. So essentially, independent reactions plus Gibbs phase rule is equal to the number of metamorphic variables. Gibbs phase rule tells you it's a bivariate situation. Bivariate means two variables need to be quantified. Independent reaction tells you you have two reactions, so two equations, no more. You don't have anything more. You have four metamorphic variables. This is, remember here, this is OR. This is OR. I think, have you understood this? This is very, very crucial to understand. Let's do a little more complex system. I will give you a problem to do. You do it yourself. I won't check it. You do it yourself. If you have a problem, let me know. What happens if I take MnO as an additional system component? You do the problem yourself. I will not tell you. Remember very carefully, I have extended it to MnO system. That means MgO-FeO-MnO. So olivine will not be MgFe whole twice SiO4, but it will have MgFeMn whole twice SiO4. So it will have Mg2, three components, Mg2SiO4, Fe2SiO4, Mn2SiO4. Three phase compounds for olivine. Similarly for orthoperoxime, Mg2Si2O6, Fe2Si2O6, Mn2Si2O6. Three phase compounds. 3 plus 3 plus 1. 7 phase compounds. 3 plus 3 plus 1. 7 phase compounds. System components 1, 2, 3, 4. 7 minus 4 is equal to 3. You will have 3 dependent reactions. You find out what they are. And what will be the metamorphic variables? I'm just giving you the clues. Next one I will go a little faster. Now you see here, for this one I am keeping the blue pen mark here. So there are 3 components. Just a clue. Mg2SiO4, Fe2SiO4, Mn2SiO4. Right? So, XMG olivine plus XFE olivine plus XMN olivine equal to 1. When you talk of metamorphic variables, from here, if I go here, then there is a problem. Problem is, out of the 3 equal to 1, 2 are independent. Any 2 are independent. 1 is dependent. If you know this 2, this is automatically done. Or if you know Mn and Fe, Mg is automatically done. So, out of the 3, 2 variables are true variables, unknown variable. The third one is a derivative. It can be determined because you already have another additional equation. So here then, this will be changed to AND. This will be changed to AND. Because the other one, XMN, is automatic 1 minus. So that is how critically you have to look at mineral assemblages. Mineral assemblages you have to look at very carefully. Well, let's take an assemblage, a very classic assemblage in many pellitic rocks. Muscovite, biotite, garnet, kyanite, quartz. Muscovite, biotite, garnet, kyanite, quartz. If I ask you to do it thermodynamically, as I have always told you, you have to ask, what is the composition of the phases? That's the first question that should come to your mind. What is the composition of your phase? Let's say I tell you, okay, the system is. Let's find out. Okay, I think I'll give you the composition. Muscovite is KAl2 AlSi3 O10 OH4 twice. Let's say this is the stoichiometric Muscovite composition, ideal Muscovite composition. You never get it, but this is ideal, near ideal. This is ideal. You get compositions close to ideal, but there are other things. We go step by step. We don't make things complex right at the beginning. It's not a good thing to do. Biotite K Mg comma Fe whole thrice AlSi3 O10 OH twice. The magnesium in member KMg3 is called phlogopite. And KFe3 is called anite. A-N-N-I-T-E. Let's say if I go to guard it, let's do it simple first. We don't make things complex. Once you understand the basics, you can make it as complex as possible. There's already a complexity here. Let's say it's MgFe 3 L2 Si3 O12. This is a very simple garnet. Pyrope, Mg3 Al2 is pyrope. Fe3 Al2 Si3 O12 is almandine. So, we have pyrope and almandine. Then you have kyanite, and as conventional, quartz is normally taken as a pure phase. So that's the composition field. That's the composition. So what is the system component? Now, how many phases? Muscovite, biotite, garnet, kyanite, quartz. You see it on the microscope, you identify muscovite, biotite, garnet, quartz. That's it. Done. Phases. What is the system component? What is the system component? So, let's say K2O, MgO, FeO, Al2O3, SiO2, H2O. Why H2O? Because of the radicals. So K2O, MgO, FeO, Al2, SiO2 system. This is called the famous KF MASH system. KMFASH. KF MASH system. So now the question is, so this is 1, 2, 3, 4, 5, 6 component system. 6 component system. So let's see what the Gibbs phase rule says. What is the Gibbs phase rule says? Gibbs phase rule. F C minus P plus 2. Components, 1, 2, system components, right? 1, 2, 3, 4, 5, 6. Number of phases. P is phases, not phase components. Phases. 1, 2, 3, 4, 5. Plus 2. 8 minus 5 equal to 3. Trivariant system. It's a trivariant system. Means what? Means there are many metamorphic variables. But whatever you do, 3 inputs are necessary. They cannot be constrained by the system itself. They cannot be constrained by the system itself. You have to get those 3 outside. And you said, Acha, when I am saying this, when I am doing this, did a thought occur to your mind? Did a thought occur to your mind? obviously these two minerals have OH2. So there must have been a fluid with H2O. We have not taken fluid as a phase. Have you understood? I have not taken fluid as a phase. Remember this. That means, since I have not taken fluid as a phase, therefore, and this is very crucial, when you practice, it should be very crucial. Since I did not take H2O as a phase, there are two things. XH2O is not equal to 1. That's very, very important to realize. XH2O is not equal to 1. It's a variable. It is a phase component which is variable. H2O is a phase component which is variable. That is a very, very crucial thing. In the phase, I did not take fluid. But I know, because of muscovite and biotite, H2O is there. But I have not taken fluid as a phase. So XH2O, this phase component, is variable. It's not 1. But if I had, before we go further, I would like to clarify one interesting thing, and that you must realize. These are very crucial, very delicate things to understand. Imagine if I took phase as 6, what phase? Fluid phase. What phase? Fluid as a phase. Now, very important. Fluid as a phase. Then what would have mean? XH2O is equal to 1. Have you understood? That's an important equation. XH2O is equal to 1 is an equation. You have put in the data. But if XH2O is not a phase, then XH2O is less than 1. You can do another thing. Think about it. You could have added, I'm writing it in red so that you remember what I'm saying. You see here, be very, very careful as to what I'm saying. I will repeat again what I said before. I have done this, I guess you understand it. But what I said was a word of caution, that in this space I have taken H as a component, but in the phase I have not taken fluid as a phase, which means XH2O is not equal to 1. Clear? XH2O, the fluid component H2O, is variable. Right. I could have done it another way. Say, for example, I could have assumed that I had H2O-CO2 fluid. I had an H2O-CO2 fluid. Then what would have happened? Now you see here, H2O-CO2 fluid. What would I have done? Just see here what happens. Very catchy. I will erase it, but just for the caution. Your system component would have added CO2. Yes or no? Because I am saying that my fluid has H2O-CO2. So your fluid component, you have to add one more here. So this would have been 7 plus CO2. And your phase would have been muscovite, biotite, garnet, kyanite, quartz, H2O, and fluid. 6. You see, I have increased C, but I have almost increased P. Your variance remains the same. That's very interesting. I have increased the number of system components. I have increased the number of phases by the same amount. Variance remains same. No change. So whether, have you understood? It doesn't change. Have you understood? Why is it not changing? Because here XH2 is a variable. For the blue part, H2 is a variable. I have not taken as a fluid phase. When you do this, H2 is still variable. H2O is still a variable. So although you have included increased component by 1 by adding carbon here, you have also increased the number of phases by adding fluid phase. So then your Gibbs phase rule says, okay, I know what you've done, but that's it. Variance does not change. Why doesn't it change? Because in the blue color, XH2 is a variable. And if you take a fluid phase, H2CO2, your H2 is still a variable. In both cases, it's a variable. Gibbs phase rule response. Your variance does not change. Right? I will erase the red part. These are very delicate things, extremely delicate. If you want to study metamorphic physical, you have to do exactly what you are doing. You could have asked me, what happens, sir, if H2O plus CO2, XH2O plus XCO2 is not equal to 1. That means there was some other component in it. Then the variance would have added to 7 as before, but phases would have been still 5. Why? Because you did not consider fluid. Because if this is the situation, then you don't have a fluid as a phase. So it's not equal to 1. So it would have been 7 minus 5 plus 2. It should have been 4. Why? Because here XH2O and XCO2 are both variables. But when you write XH2O plus XCO2 is equal to 1, then 1 is a variable, not both. Have you understood? Right. Now we go back to the problem. I'm telling you this because these are the intricacies which makes metamorphic petrology, metamorphic physicality are very complex. But if you understand the logic, it's absolutely, you can't lose marks. Not at all. Because the logic goes straight. Like an arrow. And there can be no metamorphic petrology. Either you normally get 10 out of 10 or 0 out of 10. We give you 3, 4, 5 because we are nice to you. But technically, no. Right. So we have a trivariant assemblage. That means in this assemblage, if you take what it is without a fluid phase present, this is what it is. Now we come to the question of independent reactions. IR. What is IR now? Number of phase components minus number of system components. And this we already know, the number of system components is 6. Here, number of system components is 6. Number of phase components. Now, it's the question. How many? For muscovite, it's 1 because it's a pure phase. For biotite, the number of phase components is 2. Why? Because phlogopite, ammonite. XMG plus XF in biotite equal to 1. So there are 2 phase components. For garnet, again 2. For kyanite, 1. Pure phase. For quartz, 1. Did I miss something? Yes. I missed. What is that? H2O. It's a variable. That is the point now. Suddenly you have H2O. It's a variable. It's a variable. So now we have muscovite 1, pure phase, kyanite 1, pure phase, quartz 1, pure phase, biotite 2, binary solid solution, garnet 2, binary solid solution. So we have 1 plus 2, 3 plus 2, 5, 6, 7 and 8. It says 8. It says 8. Minus 6 is equal to 2. Minus 6 is equal to 2. Have you understood? Like last time, therefore, Gibbs phase rule says 3 variables are necessary to solve your problem and they should be quantified from outside the system. This tells you you have 2 reactions, no more. So 3 plus 2, 5. There should be 5 variables. There should be 5 variables and no more. What are the variables? Look here. Pressure, temperature. Now, XFE biotite or XNG biotite. XFE garnet or XNG garnet. These are important. Did I miss something? Did I miss? Yes, I missed. Five variables. There you go. 1, 2, 3, 4, 5 variables. 5 variables minus 2 independent reactions. 3 variables unquantified. Gibbs phase rule says you have the trivariate assemblage. Yes, of course, Gibbs rule says, I told you so, that you will have a trivariate assemblage. So, Gibbs phase rule plus independent reaction, number of metamorphic variables. So when Gibbs phase rule says the variance is 3, it means 3 unquantified variables, but the actual variables are more. Namely, 5 here. Namely, 5. Later on we will see how to compute these variables. But right now you understand that these are the variables. Variables minus independent reactions is the number of unknown components. Gibbs phase rule tells you 3. You can do with CO2 and try it yourself, what you get. Unless you make a logical mistake, you will get the answers. But if there is a logical mistake, you will not be able to add it up. You will not be able to add it up. 3 plus 2 is equal to 5. You will not be able to add it up. Because they are derived from different equations. Now, let me write the reactions. For you. So, where do I write? Okay. I hope you will remember this. So, I will write the equation here. What are the reactions? Can anyone tell? Okay. Say, for example, I can give you a classic example here. Biotite and garnet both have MgFe. So I can write this is a reaction where you can see there are 2 pairs. This is pyrope garnet. On the other side of this equal to sign you have almandine garnet. So this essentially is a magnesium iron exchange between garnet. which is counterbalanced by a magnesium iron exchange in biotite. So that is one reaction. That is one reaction. It's counterbalanced. So basically, how many variables? So here what happens is magnesium Mg garnet plus Fe biotite is equal to Fe garnet plus Mg biotite. It's a magnesium iron exchange between coexisting biotite and garnet. So that takes in account one reaction. What is the other reaction? I could have left it to you, but I think I will tell you. You do it yourself, yeah? Don't just take, not this, Metamorphic Petrology, put pen on paper. Next reaction. What is it? It's difficult to find for you. You will have difficulty. I have to work with an end member. So I write. You see, there are only 2 potassium here. Occurs in 2 minerals. So if I want to write a reaction involving muscovite and biotite, there should be on either side of this reaction. On either side of the equal to sign. So I write K Mg3 Al Si3 O10 OH whole twice on this side, and on the other side I write K Al2 Al Si3 O10 OH whole twice. I'm done. I'm done. Biotite here, fluoride, magnesium end member, and here muscovite. But it's not balanced. What else is there? I can see here it is magnesium and there is no magnesium here. I look at the assemblage at the top. Magnesium is there in garnet. So if I take garnet here, and that has to be magnesium garnet, right? So I can balance this magnesium, but there is a problem. What is the problem? Here you see, 1 potassium, balanced. 3 magnesium, balanced. Wait. How many aluminiums are there? This is left hand side, this is right hand side. Left hand side. How many aluminium is there on the left hand side? 1 plus 2, 3. How many on the right hand side? 2. See, this is missing. 2 plus 1, 3, plus 2, 5. 2 plus 1, 3, plus 2, 5. Do you understand? So here is the mistake that I did. Left hand side, 2Al2SiO5. So 1 aluminium plus 2 aluminium, 3 aluminium. Here I did not count this aluminium. 2 plus 1, 3. 3 plus 2, 5. 5 aluminium. What I should do is 2Al2SiO5. And then you have 2 into 2, 4, plus 1, 5. You're done with aluminium. Now we have to check silicon again. What happened to silicon? We must have gone wrong because we took the silicon. Now let's look at silicon. 3 on the left hand side, I can see here, 3. Then 2 into 1, 2. And then 2 silicon, that's 2. So it should be 7 silicon on the left hand side. On the right hand side, it is 3 plus 3, 6 silicon. 6 silicon. So on the left hand side, let's check. Silicon 3 plus, we are checking for silicon. Okay, 3 plus 2, 5 plus 2 we wrote 7. But here, okay. So 3 plus 2, 5, and here it was 6. That means the left hand side has 1 deficiency of silicon. So if we just do this way, now let's check for silicon. Now let's check for silicon. 3 plus 2, 5, plus 1, 6 on the left hand side. On the right hand side, 3 plus 3, 6. Now it's okay. So now we have 6 silicon on the left hand side. This 2 has changed. This 2 has been brought in 2 to balance aluminium. Now we look at oxygen. Left hand side, right hand side. Left hand side oxygen, 2 plus 10, 12. Plus 10, 5 into 2, 10, plus 2, 24. Right? Right hand side, 2 plus 10, 12 plus 12, 24. Done. Your equation is balanced. Imagine the mistake that I did. Even an experienced person might make mistake. I forgot to check in this aluminium and it made catastrophe. Oh, everything would be wrong. So now we have this situation. So we now know that we have 5 metamorphic variables, out of which you have 2 independent reactions and 5 metamorphic variables. And the Gibbs-Duhem equation says 3 variables need to be input from outside the system.